We'll now look at the impact of an absorbing media. So we have some absorption in the media and how that impacts the wave function. So we'll look at absorption. And the idea here is I have a certain incoming intensity of light at position x. So I call what's coming in here, this line is at x. And so what's coming in is the intensity at x. And I've got an absorbing media, so it absorbs some of the light inside. Maybe there's a smoke filled in this region, and not all the light makes it over through this distance delta x. So it absorbs some of it and deposits that energy inside here. By the time it gets over to here, it's really the intensity at x plus delta x. So if this is x, then this will be x plus delta x. And then I'm going to write that in this form. It's going to be the intensity at x plus the change in intensity as it goes across this delta x. And this change of intensity could be positive or negative. If it gets amplified, it would be positive. If it gets absorbed, this thing should turn into a negative number. And now I can use some sort of common sense physical reasoning that that if it's absorbing it, it's going to lose intensity. And one would expect the more that I have here, the bigger the change would be over here. Okay, I would have in magnitude, and then moreover, that the bigger this distance is, it's going to absorb more. So the change in intensity should be proportional to the incident intensity. The greater the incident intensity is, in practice, more gets lost, and it's also the distance proportional to this distance. And since we're looking at absorbing media, then it actually loses it, and so I'll reflect that here. I can rearrange those deltas, divide through by delta x, and get this expression. And now then take the limit as delta x gets very, very small, and I get this differential equation where alpha is just a coefficient of absorption that characterizes this media that is absorbing this energy. Separate variables, so divide through by I, multiply through by dx. So I've got variables separated. Integrate both sides. I can do an indefinite integral, so this is natural log of I from here. And minus alpha dx becomes indefinite integral minus alpha x. And then I pick up an integration constant, which I'm just going to write natural log of a for the time being. Now then, this integration constant a here, I can satisfy by assuming that what's incident over here is I naught. So at x equal to 0, the intensity is all the intensity I naught. So if I plug in 0 here and set the I of 0 to be I naught, I just simply get that this constant A is I naught. And so the intensity falls off like minus e to the minus alpha x. Excuse me. Then if you look at that, I can rearrange this to be I over I naught as e to the minus alpha x. But I also know that I over I naught, remember, the intensity is proportional to the amplitude squared times the frequency squared times the wave velocity. Amplitude squared at A naught, omega squared, I naught is proportional to A naught squared, omega squared, and so these will cancel. And so I get this ratio in terms of amplitudes would be here. And so I can set these two equal. I over I naught, well, I is just I over I naught is just I is I naught e to the minus alpha x, so that's here, and I naught is just I naught, so the I naughts will cancel, and I get e to the minus alpha x, and that's on this side, And over here I get A squared over A naught squared. The amplitude squared going out is the amplitude over the amplitude squared going in. Has to be in that same ratio from equating these two expressions. And with that, I can solve this for A squared. Just multiply through the A naught squared. And then finally take the square root of both sides. And the square root is A naught, and this is e to the minus alpha over 2x. And so one gets that the amplitude falls off as the initial amplitude as e to the minus alpha x. The larger it propagates into the medium, the amplitude drops accordingly in this exponential fashion. And what's interesting is the amplitudes go as minus alpha x, that's with this being the absorption coefficient, but the amplitudes, because they're related essentially by the square, the intensity is proportional to the square of the amplitude, the exponential factor here is half that value, and it falls off exponentially half as fast. Well, putting all of these things together, I could write the total radial wave, if I have absorption and it's propagating out in these spherical wavelets, is of this form: an A naught related to the amplitude, e to the minus alpha x times that accounts for the absorption. This accounts for the 1 over r squared fall off in the intensity. And then I could have an outgoing wave with the minus sign radially going outward, or one going radially inward. The radially inward going waves are not real common, and so most of the time we will take this expression with the minus sign, and of course we could always have a phase shift here to be the general expression in arbitrary absorptive media of what the wave, a spherical wave, propagating from a point light source or central light source for us.